Hello everyone, I welcome you all for the first session of the new chapter Electromagnetic Waves. From the second PUC Physics, this chapter Electromagnetic Waves will be asked for 3 marks or sometimes 2 marks. There will be a question from the first main, second main or in the third main. Okay. So, this chapter carries 3 marks and the questions may be asked in the first, second or third main. Okay. First of all, let us understand what are electromagnetic waves. We know that when you place a static charge, in space, this charge can produce electric field around it, correct? A static charge can produce an electric field around its space. Similarly, when you consider a conductor, in a conductor, the charges or the electrons are moving. So, all the electrons are having a common velocity which is called as a drift velocity. So, these electrons under motion can produce a magnetic field around it. Okay. A static charge produces electric field. A moving charge, a charge which is moving with a uniform velocity or a constant velocity, that can produce a magnetic field around it. And from the 6th chapter, you have learned about the Faradays Loss, correct? Faradays Loss. Faradays Loss says that time varying magnetic field can induce an EMF. EMF is nothing but an electric field. Okay. See, Faraday's laws says that the time varying magnetic field can induce an EMF. EMF is nothing but an electric field. So, a time varying magnetic field is producing an electric field. The converse is also true. Means the time varying electric field can induce a magnetic field also. Okay. So, time varying magnetic field is inducing an EMF which is nothing but an electric field. In the same way, a time varying electric field can induce a magnetic field also. So, by all these observations, Maxwell concluded that the variation of one field with respect to time can induce a other field. That is, the variation of electric field can induce a magnetic field, or the variation of magnetic field can induce a electric field. So, this is his observation and he concluded that the variation of electric field or magnetic field generates electromagnetic disturbance in space. So, this is the conclusion given by James Clerk Maxwell. Maxwell concluded that the variation of electric field and magnetic field generates the electromagnetic disturbance in space and which propagates in the form of electromagnetic waves. Okay. The variation in electric field and magnetic field in space creates a electromagnetic disturbance. So, that electromagnetic disturbance is propagating in the form of electromagnetic waves. Now, we should look at how we can represent an electromagnetic wave, the representation of an electromagnetic wave. Let us write the representation of electromagnetic wave. Representation of electromagnetic waves. It consists of electric and magnetic disturbances the electric and magnetic field vectors which are propagating in space. Consider this as y-axis, this is z-axis, and this is x-axis. Now let us represent a wave. Let me represent electric wave vector in xy plane. So look at this diagram. This is the representation of a plane electromagnetic wave. So how do we write the plane electromagnetic waves here? See here. This is an electric field vector which is a sine wave. So you have to look at this electric field vector. This electric field vector is a sine wave which is propagating in an xy plane, and this is a magnetic field vector, and this magnetic field vector is propagating in xz plane. You can look at this. This is z axis, and this vector, the magnetic field vector, which is represented by B. So this is propagating in an xz plane. Therefore, the electric field vector, which is a sinusoidal wave, and a magnetic field vector, which is also a sinusoidal wave, they are propagating perpendicular to each other. Correct? So in a space, if you consider electric field vector and a magnetic field vector, they are propagating in a space such that they make an angle of 90 degrees with each other. Okay? And very importantly, this electric field vector and magnetic field vector, they are in phase. There is no phase difference between these two. Okay? And the propagation, the direction of propagation of electromagnetic wave is concerned. So though the direction of propagation of this wave is perpendicular to both electric and magnetic field vectors. See, the direction of propagation is towards the x-axis. So this is the general representation of a plane electromagnetic wave. So what does it consist of? What does the plane electromagnetic wave consist of? It consists of electric field vector, it consists of magnetic field vector, and these electric field vector and magnetic field vector are coupled together and they propagate perpendicular to each other in phase. And the direction of propagation of this wave is always perpendicular to both electric and magnetic field vector, which is in this direction. Okay? Now we have to write the proper definition for the electromagnetic wave. So what is an electromagnetic wave? If the question is asked, what is an electromagnetic wave? So what do you have to write? See, the definition is like this. The sinusoidal variation of electric and magnetic field vectors which are right angles to each other, propagating in space perpendicular to both electric and magnetic fields. So how do we define electromagnetic waves now? The sinusoidal variation of electric and magnetic field vectors which are right angles to each other. Correct? See, electric field vector and magnetic field vector are propagating in space right angles to each other. They are perpendicular to each other. Right angles to each other, propagating in space in a direction perpendicular to both electric and magnetic field vectors. So the direction of propagation of this wave is always perpendicular to both electric and magnetic field vectors. So this is how you can define the electromagnetic waves. Now we should write what is the source of electromagnetic wave. Let us write that. Source of electromagnetic magnetic waves. So this might be your 1 mark question. So in your examination they may ask this question for 1 mark, like what is the source of electromagnetic waves? The source of electromagnetic wave is nothing but an oscillating charge or an accelerated charge. Accelerated charge. See, what is the source of electromagnetic waves? The source of electromagnetic wave is nothing but an oscillating charge. Okay, you know what are oscillations? The to and fro motion. If you have a charge here, if this is a charge Q, and this charge is moving in an oscillatory motion, the to and fro motion like this, it may oscillate like this. So this is a to and fro motion. So an oscillating charge can produce an electromagnetic wave. A charge which is moving with a uniform velocity or a constant velocity can produce electric and magnetic field which are not varying fields. Okay. In order to get a varying field, okay, in order to get a varying magnetic field, we need to have this accelerated charge or an oscillating charge. Even oscillatory charge is also an accelerated charge, correct? So if we give an example for this, okay, what is this accelerated charge or what is this oscillating charge? If you give an example in LC circuits, inductance, capacitance, correct? LC means inductance, capacitance. So in LC circuit, the charge oscillates between the plates of a capacitor. Therefore, LC circuit emits electromagnetic wave. Okay. So if you give an example for this oscillating charge, so where we can have an oscillating charge which emits the electromagnetic wave. So in an LC circuit, inductance capacitance circuit, in this LC circuit, the charge oscillates between the plates of a capacitor. That is why it is an oscillating charge, correct? So this oscillating charge is producing an electromagnetic wave. And what is the one more case we can write where the charge is accelerated? When an electron jumps from higher energy level to the lower energy level in an atom. Okay. So this is an accelerated charge. An electron is jumping from higher energy level to a lower energy level, so that can emit the electromagnetic wave. See, light is also an electromagnetic wave. Okay, light is also an electromagnetic wave. So when an electron jumps from higher energy level to the lower energy level, which can emit the light energy, but light energy is also an electromagnetic wave. When electron jumps from one energy level to the another, which can emit the electromagnetic wave. So one more case if you write, when a fast moving electron hits the metal target, can emit X-rays. Okay. When a fast moving electron is hitting a metal target, which means it is decelerated. Okay, the speed is decreasing or increasing, which is nothing but a change in velocity, correct? So when a charge or when a fast moving electron is hitting a metal target which is decelerated, so that which can also emit a X-rays. So X-rays is once again a electromagnetic wave. So electromagnetic waves is produced by oscillating charge or an accelerated charge. So what are the examples of oscillating charge or an accelerated charge? First one, in LC circuits, the charge oscillates between the two plates of a capacitor, so that can emit a electromagnetic wave. Secondly, when an electron jumps from higher energy level to a lower energy level, which can emit a electromagnetic wave. And here in this case, when a fast moving electron is hitting a metal target, then it can emit the X-rays, which is nothing but an electromagnetic wave. Fine. Now we will move on to the next topic, that is the nature or the characteristics of this electromagnetic waves. Let us write the nature, characteristics of electromagnetic waves. First one. See, I said that electromagnetic waves are nothing but the waves which are produced due to the sinusoidal variation of electric and magnetic field vector, which are coupled together in phase and they propagate in a direction perpendicular to electric and magnetic fields. So this is what we called as an electromagnetic wave. So if we find the speed of electromagnetic wave, so what is the speed of electromagnetic wave? See, the speed of electromagnetic wave is given by C is equal to 1 over root of mu naught into epsilon naught, where mu naught is permeability of free space and epsilon naught is permittivity of free space. See, the speed of electromagnetic wave depends on the nature of that medium or the electric and magnetic field properties. This epsilon naught is related to the electric field vector and this mu naught is related to the magnetic field vector. So the speed of that electromagnetic wave is depending on the nature of that medium. In air or free space, the speed of electromagnetic wave is given by C is equal to 1 divided by root of mu naught into epsilon naught. So if we substitute the values of mu naught and epsilon naught, what do we get is the value is equal to 3 into 10 to the power of 8 meter per second. So this is nothing but a speed of light in vacuum, correct? So this equation proves that a light is also an electromagnetic wave. Okay. So the value of mu naught and epsilon naught, if we substitute, what do we get in the final result is 3 into 10 to the power of 8 meter per second. So that is why this speed is nothing but a speed of light in air or vacuum, and you can say that light is also an electromagnetic wave. Next, the speed of electromagnetic wave in a medium. If the electromagnetic wave is traveling in any other medium other than air or vacuum or free space, what is the speed? The speed is given by V is equal to 1 divided by root of mu into epsilon. Okay, root of mu into epsilon, where mu is the permeability of the medium and epsilon is the permittivity of that medium. So the speed of an electromagnetic wave depends on the medium. Okay, fine. The second property is the electromagnetic waves are transverse in nature. Transverse in nature. Okay. So I said that this electromagnetic wave is having electric field vector and magnetic field vector. They are perpendicular to each other and the direction of propagation is perpendicular to both electric and magnetic field vectors. That is why this wave, so we have represented a plain electromagnetic wave here. So this wave is nothing but a transverse wave. Okay, transverse means the direction of propagation is perpendicular to these two vectors. Okay, these two vectors. So therefore electromagnetic wave has a transverse nature. Okay, and I said that this is electric field vector and this is a magnetic field vector. So what are the values of this electric and magnetic field vectors? the electric field vector is given by E is equal to E naught into sine of kx minus omega t. So that's an expression for this electric field vector. E is equal to E naught into sine of kx minus omega t. And the value of magnetic field vector B, which can be written as B naught into sine of kx minus omega t. A very important observation here is the ratio of E naught to the B naught. So what are these E naught and B naught? They are the maximum displacements of these vectors. See, this is called as an amplitude of the wave, correct? This maximum displacement is called as an amplitude of the wave. So the amplitude of electric field vector E naught and the magnetic field vector B naught. So their ratio will give us a speed of light c. Okay, E naught by B naught is equal to c. This is a very important equation. E naught by B naught is equal to c. Fine. So in this expression, E is equal to E naught sine of kx minus omega t and B is equal to B naught into sine of kx minus omega t. Here the value of k is equal to 2 pi by lambda, which is called as an angular wave number. This k is equal to 2 pi by lambda and this k is called as an angular wave number and this lambda is called as the wavelength of the electromagnetic wave. Okay, and also this omega is equal to 2 pi f. Okay, omega is equal to 2 pi f, where this f is the frequency of the electromagnetic wave. So omega is the angular frequency and this f is called as a frequency of the wave. Third one, electromagnetic waves carries energy and momentum. Electromagnetic wave carries energy and momentum. The next property is the electric field vector which is responsible for the optical effects of electromagnetic waves is called light vector. See, this is a one mark question for you again. Okay, in your examination they may ask what is a light vector. The electric field vector which is responsible for the optical effects of electromagnetic waves, this is called as a light vector. See, we said that electric field vector is a sinusoidal variation of electric field. So this electric field vector is responsible for the optical effects, like light undergoes reflection, refraction, interference, diffraction, polarization, so on. So those are the optical effects of electromagnetic wave. A light vector is the one which is responsible for optical effects. So those the electric field vector which is responsible for these optical effects is nothing but a light vector. So this is a one mark question for you. Next property, electromagnetic waves are undeflected by electric or magnetic fields. Electromagnetic waves are undeflected by electric and magnetic fields. Okay, by applying electric field or magnetic field, we cannot deviate the path of electromagnetic wave. And we have one more property, the last property, radiation pressure. So what is a radiation pressure? I said that electromagnetic waves consist of energy and momentum, correct? So in this property we said that electromagnetic waves carries a energy and momentum. That is why when it is falling on any surface which exerts a pressure on that surface, the pressure exerted by this electromagnetic waves on the surface which falls, which is called as a radiation pressure. Yes, these are the important properties of electromagnetic waves. Okay, so we'll see one by one. The speed of electromagnetic wave in a space is given by an equation C is equal to 1 over root of mu naught into epsilon naught, where mu naught is the permeability of the free space and epsilon naught is the permittivity of the free space. That is why the speed of electromagnetic wave depends on the nature of that medium, electric and magnetic properties of the medium. Next, whenever it is traveling in a medium, the speed is given by V is equal to 1 divided by root of mu into epsilon, where mu is the permeability of the medium, epsilon is the permittivity of the medium. Then electromagnetic waves are transverse in nature. You can see in that diagram only the propagation, the direction of propagation is perpendicular to both electric and magnetic field vectors. That is why this is having a transverse nature. And very importantly, we deduce that E naught by B naught is equal to C, which is equal to the speed of light. And then electromagnetic waves carries energy and momentum. The electric field vector, this point is very important for you. The electric field vector, which is responsible for the optical effects, is called as a light vector. Okay. Then electromagnetic waves are undeflected by the presence of electric or magnetic fields. And then radiation pressure. So the pressure exerted by the electromagnetic waves on the surface which falls, which is called as a radiation pressure. Okay. Yes. So that's all for this session. In our next session, we can discuss the electromagnetic spectrum, the different ranges of frequency and wavelength of electromagnetic waves, and also the property and the applications of it. Until then, thank you.